When you think about security, you have to think about two types of attackers, the economically motivated attackers and nation states. And you have to have distinct strategies for defending against these two types of parties.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff, your host for Season 3. We are at risk. Our personal data, our company's intellectual property, and even government secrets are under intense pressure from hackers. Nothing is safe, not even our ICs. Wars have literally been won and lost thanks to security, or a lack of security, on hardware chips themselves. Today in the lobby, to kick off Season 3, we're joined by someone who has made it his personal mission to stop hardware hackers in their tracks and make your electrical chips as likely to give up secrets as my potato chips. Serge Leaf is DARPA's program manager for the Microsystems Technology Office. After spending decades as an engineering leader in the design, automation, and hardware simulation world, including almost 30 years as a general manager and VP at Mentor Graphics, he gave it all up to focus on growing and expanding hardware security at DARPA. If you're not familiar with DARPA, the Defense Advanced Research Projects Agency, you need to know who they are. DARPA was founded as a response to the launch of Sputnik in 1957 as a program to promote collaboration between the US government, academia, and industry. The Economist called it the agency that shaped the modern world. Now that's a big claim to make, but DARPA has had a hand in inventions you maybe have heard of, like the internet. Remember ARPANET? That's DARPA. It's also had a hand in GPS, graphical user interfaces, weather satellites, Moderna's COVID-19 vaccine, drone tech, stealth tech, voice interfaces like Siri, and the list goes on and on. All of those came from DARPA programs and program managers like Serge, who, by the way, holds patents in hardware Trojan detection and IoT infrastructure. Serge, thank you so much for being here today. Before we dig into hardware security, can you tell us about your background and how you got into engineering?
Yeah, well, thanks for having me. And sure, so I was born in Soviet Union in Moscow, and I lived there until the age of 15 or so. My family was from this class vaguely known as intelligentsia, which meant like intellectuals and professionals and so on. So I had a very happy, pleasant childhood, aside from the fact that, with age, my awareness of living in totalitarian dictatorship that was truly evil sort of was growing and escalating. So by the time I was 15, I was pretty anti-Soviet. And so my parents fortuitously chose to left the Soviet Union approximately at that time, because I would have definitely been on trajectory of some kind of collision with the state. So we left when I was 16, and we settled in Arizona, in Phoenix. My dad was an industrial engineer who worked for Motorola most of his career. So I grew up not grew up, but from the age of 16 or so, lived in Phoenix, finished high school there. The Soviet educational system, in my opinion, was so strong on math and sciences that I was able to finish high school in 2 years, even though I literally spoke no English on day one of starting high school. And went to Arizona State University for bachelor's and master's degrees, bachelor's in electrical engineering, master's in computer science.
And then where did you go after school?
Between the third and fourth year of college, I applied for and was surprisingly hired by Intel for a summer internship. I am stunned that they hired me because literally I knew nothing. The current version of me would never have hired me. So it was really striking that they hired me. So when I was shown to my first cubicle at Intel, the guy who showed me there, he said, "Oh yeah, by the way, this cubicle has a story. The pressure's on you now." And I said, "Well, what's the story?" And the guy said, "Well, last summer we had a summer intern whose name was, I'm not going to mention. And this summer intern, apparently it wasn't even his job. He's the one who architected and designed the microcontroller that became the highest volume part that Intel has ever sold." And so I thought, okay, well, it's so interesting. So I'm going to do something like that. I hope I can do something of that magnitude. But so my actual job was relatively straightforward. So what I ended up doing is my arrival sort of coincided with arrival of Ethernet. And the way that the chip design was done is most of the simulation was done on one type of computer. Most of the graphics design was done on another kind of computer. And so when you wanted to do some kind of analysis, you had to pick up the phone, call the people in the operations and say, make the tape of this design. They made the tape, carried it across the room from one machine to another, loaded it, and then the design engineer could run the software that he wanted to run on. And then the results were once again loaded onto the tape, carried across the room. So I looked at it and I thought this is pretty stupid. So I wrote two device drivers and the two prototype Ethernet boards that just arrived. And then I created this system that allowed the design engineers to basically push a button, have all this round trip made. The simulation would be executed, results would be loaded, and it would look like, this is like cloud of 1980s, right? It would look like things actually happened on your local machine, and you would get results right away. And what had huge impact on me is that this ultra brilliant hardware people that I was supporting with this, they were completely blown away because they viewed software as some kind of magic. So they were all hardware people. Software, they was something black box. They didn't understand this. And this was like probably one of the most rewarding experiences of my career, where these people that I grew to admire almost instantly once I met them were jumping up and down with excitement over something that I did that was seemingly simple and straightforward. And so that really kind of set me in that particular direction of design automation, because I wasn't really even thinking about it before that event had occurred. And so one thing led to another, and I ended up going to Intel after I graduated.
And you were not just a software person at Intel. I hear your hiring may have been a bit historic. Is that true?
Yeah, so I was basically the first software guy that they hired into Intel Chandler, and it was kind of amazing to break through into this world. I honestly felt like I really didn't belong with these guys who were intensely technical. I think Intel at that time was really kind of getting its momentum, and the magic was is they hired this ultra bright kids, quote unquote, and allowed them to do serious design work. But Intel also had some rough edges to it. My very first one-on-one with my very first manager was sort of instructive. We sat across the table. He looked at me and he said, let me tell you, Serge, how this thing is going to work. And he said, we're not friends. We will never be friends. You will do things that make me look good, and I will reward you for it. And that's the basis of our relationship going forward.
Ah. Coming into Intel as a software engineer, maybe that wasn't the title at the time, but a software person surrounded by hardware folks with a manager that was basically saying, just make me look good and I'll reward you for it. Did you feel like you were maybe digging yourself out of a hole or a black sheep there? Or
So after me, they started hiring more and more software people. So software engineering became a growing community over there. But I always felt like we were second-class citizens in that world.
Interesting. So then you leveraged chip design into a storied career at Silicon Graphics, later Mentor Graphics. Can you briefly describe what you did there, and then we'll talk more about your DARPA stuff?
So Silicon Graphics was a pioneer, also based, by the way, full of ex-Intel people. It was a pioneer in high-speed, photorealistic, full-motion graphics. And that was really enabled by this ultra-complex geometry engine, which was a 9-chip graphics pipeline where each of the chips did the lighting, texturing, different steps in the rendering process that ultimately resulted in million frames being output to the video display and so on. SGI had a pretty funky culture, and one of the elements of that culture was that they required that their own hardware be used for design of everything that they do. And so in those days, design automation companies, of course, wouldn't support something exotic like SGI hardware. And so what that left me with as the manager of the design automation operation at Silicon Graphics is they basically forced me to create a custom environment for designing of next generation SGI systems that had to be based on SGI hardware. And so I had a team of like, I don't know, 15, 20 people, and we basically were expected to replicate the same kind of functionality that was being sold by, Mentor, Cadence, and Synopsys. And it was pretty rough. I ended up architecting and implementing their synthesis system and high-speed simulation system, which what they really wanted to do was to see this next generation 9-chip pipeline operate in simulation. The team was full of mathematicians who were really interesting and unusual and different to work with because they think about the world differently. And so, even understanding what they were saying was challenging. And then translating this into software was pretty interesting exercise.
And then you went on to spend almost 30 years at Mentor Graphics. Can you tell me more about that role and what that transition was like?
So for the first time, I was actually finally in the EDA company, as opposed to being previously always EDA person stuck in the initially chip company and then systems company. There was one fun and kind of formative experience for me. This story sort of began with the change of CEOs at Mentor. And the new CEO came in and he did his kind of world customer tour where he asked questions of the key customers, like what are we doing well, what are we doing poorly? And what he got back universally is that designing ASICs is, we pretty much understand how to do this and your tools are adequate for that. But the issue that we have is hardware-software integration. Can you do something about this? And so the CEO came back, and I've been the one advocating for this type of technology in the company, and so he specifically approached me, and me and one other guy went and essentially were asked to draft a business plan to do something about this gap. And then the business plan was approved. The company gave me something like $1.9 million in 1 year to create this product. And it came with, we don't know we don't think you're going to be able to do it in 1 year. We don't think, big companies can turn that quickly. It's a huge problem. And so they were not expecting us to succeed. To make the long story short, it became a very successful program. But that was an interesting experience where they basically gave me the keys to the car and say, figure out how to get from point A to point B.
Stick around after the break because we're going to look at how the US government is addressing hardware security. Support for this podcast comes from Infineon Technologies, a world leader in semiconductor solutions with a mission to make life easier, safer, and greener by linking the real and digital worlds through microelectronics. Infineon's Power and Sensing Selection Guide provides a comprehensive selection of MOSFETs, wide bandgap semiconductors, IGBTs, gate driver ICs, intelligent switches, sensors, and more. To find the best fit solutions for your design needs, visit www.infineon.com/power sensing selection. Serge, now you find yourself working for the government in a critical role. Did you ever think you'd work for the government, and what do you do with DARPA?
It's actually a critical role and critical time for the nation in this particular field. So I never once thought about working for the government until fairly recently, I would say. So the way this came together was kind of an interesting story. The latter years at Mentor, I was running kind of a venture capital incubation portfolio along with a division that I had. And in my portfolio, there was an in-house startup that focused on secure silicon, or basically hardware security. And so until then, I really never had any reason to go to Washington. I've been there like twice as a tourist up to that point over the course of previous 25 years. But once I had this security startup, it was important to start talking to the government to understand what they think is important and so on. And so I started coming to DC every once in a while. And on one of these trips, I ended up in this small conference for defense industry. At the very end of this conference, they had a town hall meeting. And the challenge question in this town hall meeting was China is investing $155 billion to prop up their microelectronics industry. What should US public policy response be to this? And I was sitting in the back and I was listening as different people picked up microphones and sputtered utter things that didn't make sense. I'm trying to stay away from more accurate characterization of what I heard. And finally, I couldn't help myself, so I grabbed the microphone and I basically said, look, we have an asset in the United States, and this asset is people are intrinsically entrepreneurial. People are willing to take chances, and there are a lot of entrepreneurs who are interested in advancing technology in semiconductors, which is the area of interest. What they're lacking today is there is literally no investment going into early rounds of semiconductor startups. And so I made this impassioned speech of 3 minutes, and I said, so even a relatively small amount of money could change the economics of all of this. And so I said my piece and left. And I was going to fly back the following evening, but when I got to my hotel and checked email, I had an email from somebody who was an administrator for Deputy Secretary of Defense, who said in that email that Deputy SecDef was in that town hall, heard what I had to say, and wondered if I had time to come to the Pentagon the next morning at 10 o'clock to continue the conversation. And so I was planning to just go see the monuments that day because the flight back to Oregon was at 5 o'clock. So I said, yeah, I think I can work that into my schedule. So I went, I came to the Pentagon, got shepherded to the conference room that belonged to the Secretary of Defense. I think at the time, Ashton Carter. This was during the Obama administration. I entered this room and there's like 30 or 40 people around this huge table wearing suits and ties and introduced themselves. I'm so-and-so from Department of Commerce. I'm so-and-so from Treasury. Like basically a bunch of grown-ups, and Deputy SecDef says, so I heard you speak yesterday. Can you please give us more details about your ideas? And I'm like, oh my God, under normal circumstances, I don't go to the bathroom without PowerPoint, okay? And here I end up in a very important meeting with no shred of presentation material. And so I ad-libbed about this concept for about 45 minutes. They asked really good questions. And then when it was over, the Deputy SecDef approached me and said, well, we really appreciate your time here. If we put together a mechanism like what you just described, would you be interested in coming and helping us run it? And I thought, like, what are the chances of this happening? So I said, sure. So I just didn't think there was any chance of that taking place. So that's how this thing started. And then I had they would contact me and say, we're doing this white paper, we're doing this briefing, can you provide some ideas, inputs, and so on. So this low-level dialogue has continued for a little bit. And then they said, it would be really great if you could join DARPA. That's where we could be doing all of this from. That is the place in the government that has the greatest nimbleness and freedom to pursue unusual things like what you're talking about. And then my dialogue with DARPA has begun. And then DARPA decided to bring me in, and I had to go through a very long security clearance process. And as this was all going on, I still didn't think this was going to happen. I just thought that this like no way this whole thing comes together. Something is going to go wrong. I won't get clearance or whatever. But what actually ended up happening is the company I was working for, Mentor, got acquired by much larger company. And that triggered all kinds of favorable elements in my compensation package on that side. So I ended up having a path to a very lucrative exit as a result of that acquisition. And so that made the financial aspect of working for the government basically irrelevant. When the clearance came through, it was kind of a unique confluence of circumstances. And I always felt this deep sense of appreciation for the United States and felt like this was my opportunity to do national service and to give something back to the nation.
So instead of sitting on a beach, you end up taking a role with, I presume, a reasonably high security clearance, doing silicon investment for the government, or what is the role here? Because obviously, it's you mentioned security.
I would liken the DARPA role as kind of probably the most similarity it has is to the venture capital role. So in essence, every DARPA program manager is like a managing partner of a venture fund with a particular theme. There's grand total of 75 program managers. I believe it can go as high as 95, but beyond that, it requires congressional approval. So DARPA building is 1,400 people. Of them, 75 are program managers, and the rest is support personnel. And so each PM comes in with their own vision. So they're basically hired not to do a particular job, but to pursue their vision. And they're chosen for the vision that has impedance match with what DoD and DARPA are interested in. So in essence, you're brought into this thing and you have, for all intents and purposes, almost infinite financial resources available to pursue your vision. So if this isn't the dream job for a technologist, I don't know what is. And also, it is missing the unpleasant aspects of being a venture capitalist, which is, having to slam companies together or send them into structured bankruptcies or sell them when they don't pan out. And, so here, the investment thesis is very straightforward. Anything that DARPA invests in has to benefit national security and economic competitiveness. Okay? Given that loose guidance, in my area of expertise, I have several portfolios. So one of my portfolios is secure silicon. So how do we make future chips secure? The next portfolio that I have is next generation design automation. How do we truly revolutionize the way that chips are designed? Another portfolio I have is domestic microelectronics. How do we establish capability to make state-of-the-art silicon in the United States, something we've gradually lost, specifically state-of-the-art silicon for Department of Defense. And I have another set of loose projects beyond that. So, but in essence, what I'm running is about $350 million portfolio. I have personnel that consists of essentially, you could think of those people as sub-portfolio managers who are also deeply technical. The other observation I have made is that this job is sort of similar to being, I guess, an executive in the movie business, where you have a constant stream of people pitching ideas to you. And it's, to quote the character of Tim Robbins in the movie The Player, what he says in that movie is, I hear 12 pitches a day, but I have enough money to pull the trigger twice a year. And so this is sort of, this has some similarities to this. And so one of the things that ends up happening in this is that the BS filter becomes, kind of hardened. So when people pitch ideas to me, I say, whoa, slow down. Here's what we want. What, why, and how. 25 words or less, please. Okay, that's what if you can get my interest in that, we can go deeper. So that's that's sort of the essence of DARPA. So everyone at DARPA comes in with their own vision that they want to execute. And some people, some PMs at DARPA are deep scientists, and they are principally interested in moving science forward in their direction. People like me, I think I'm maybe quite unique at DARPA because I'm a combination of venture capitalist, corporate executive, technologist, and now apparently a government bureaucrat. So kind of a unique mix of capabilities. So everything I work on is focused on transition, meaning I don't want to end up developing something that ends up on the shelf. I want things that I invest in transitioned either into commercial or military use during the program, not after the program.
Understood. So, what makes a good pitch, say, for secure silicon? How do you parse the good stuff from the fluff?
Well, so silicon hardware security is a kind of a funky area. When I came to DARPA 3 years ago, we had three program managers that were funding some activities in that space. And all three of us had very different views to even how to organize the taxonomy of hardware security. And so I felt the very first thing I needed to do is to get my two peers on the same page with me to at least start using common taxonomy and common language to describe what we're trying to do. And so what I ended up championing is the security model that has 4 attack surfaces. And then all the stories about how to address those attack surfaces is each attack surface is essentially an umbrella, a container for multiple things that you can and should do. So the first attack surface is supply chain security. The second attack surface is side channel attacks. The third one is reverse engineering. The fourth one is malicious hardware, also known as hardware trojans. And so each one of those things represents a huge exposure to both commercial and defense electronics. And so we have activities in every one of those areas. So for instance, let's talk about supply chain security. And you asked me about what would get my interest. Okay, so today there is a particular set of strategies that can ensure security of the supply chain by embedding something called security engine and unique identity system into the chip. And today it takes 500,000 gates to do it. So it's relatively expensive. It's a substantial amount of circuitry and real estate that is trivial if you look at Intel and NVIDIA type of processors. It's overwhelming if you look at a lot of government electronics. So if somebody came to me and said, I have a solution on how to do this with 10,000 gates, I'm interested. So something that substantively moves technology and makes it more transitionable is of instant interest. Every one of the security mechanisms comes with a cost. Reverse engineering, we have great strategies to prevent reverse engineering. It comes at a cost. The cost manifests itself in silicon area, performance, power consumption. If somebody can come to me and say, I can essentially eliminate all the cryptography emissions at with zero power budget and no impact on silicon area and minimal impact on performance, I'm interested. So in other words, if they have ideas on how to solve the problems that are real problems more efficiently, that's one angle. Or if somebody comes up with a scheme that makes a particular attack surface much harder to attack, irrespective of resources, that's also interesting. So that's on the security side. If you talk about EDA, if somebody comes to me and says, well, today, speed of simulation is, I can simulate 10 cycles per second. That's the kind of state of the art, between 10 and 100 cycles per second. But some entrepreneur comes to me and says, I can do it I have a technology that will do it at 10 million cycles per second. That's fine. That's the 25 words I'm interested. Now I want to know more. Now I want to know how. And and with a lot of these problems that we're pursuing in my portfolio, we are actually proactively asking the community these questions. So I have one of the programs where that's the challenge question. How can you use cloud and high performance computing architecture to get me 10 million cycles per second out of simulation? So it sounds like kind of a crazy question, but it turns out there's no such thing as a crazy question in the DARPA world. there is another topic that the EDA industry has tried to address for 25 years. I'm not going to name the topic, but without much success. Starts and stops and so on. At DARPA, I created a program that stipulates essentially the same challenge, which previously was not a solved problem. And I got slammed with proposals from people who have not previously thought about this problem that were fascinating. And out of the huge number of proposals, we chose 5 that any one of those, if it works, it would be transformational. And this proposal is coming from people other than me who had thought about this problem for 20 years. These are coming from people with fresh perspectives. And this is, in fact, one of the best things about DARPA is that what I really enjoy doing is dealing with the academic researchers who are generally very smart people, but in my opinion, their behavior is governed by misaligned incentives. Their incentives are to publish papers and to earn tenure. And the type of papers they publish really don't necessarily, help with my 2 reasons for being here, which is national security and economic competitiveness. So what I really enjoy is sitting down with this ultra smart people and helping direct their thinking towards the problem that are worth solving, as opposed to problems that get them closer to tenure. Which actually the problems that I have may also get them closer to tenure, but they actually lead to solving real problems that are of relevance to the nation. And so for me, this is probably the most rewarding part, is sitting around with people who are really, really smart and suggesting to them, have you looked at doing it this way? And seeing a spark go off and instantly seeing them coming up with a dozen ideas about how that particular strategy could be pursued that I have never contemplated.
Can you get into the nitty gritty a little bit of how secure is hardware today, and what are things that we as engineers should be thinking about to make sure our designs are more secure?
So I would say that most of the chips today are not particularly secure. And the way you have to think about this is there are 4 types of people that do chip designs, 4 types of companies. And in each case, it's a little bit different story. So let's look at the top of the pyramid, where we have huge merchant semiconductor companies. For them, making their chips secure is a high priority thing. There's a direct link to business. There's direct link to reputation. There's no question that their chips must be secure, and there are strong economic incentives to do that. You know which companies I'm talking about, the companies that produce mass volumes of high complexity chips. So those companies invest heavily in bespoke security solutions. They have hundreds to thousands of engineers that create custom security solutions that go into their chips. And they're spending a lot of money on this, and they're getting something out of this. Then you start looking at the next layer. The next layer is, I would say, mid-sized semiconductor companies and systems houses that design ASICs. Now we start entering the territory where there is not a lot of security expertise. There are not a lot of practices in place to make things uniformly secure. And the economics do not have clear benefit, because they're going to say, so what if we don't do it? What's the big deal? In other words, so these people won't be awakened into action until there's some crisis that occurs that hits their product line, and then they will be interested. Okay, then there's the next layer of companies, which I would call defense industrial base. These are the people that are defense contractors, and they have significant security expertise for hardware, but that security is uneven and is viewed as more like a craft than engineering. So in other words, they will design secure chips if they are told to do so, but they will charge the government extensively for that, and there are no repeatable or scalable practices there. And then lastly, you have let's just say call them IoT companies. These are the intelligent doorbells, the smart lawn sprinklers, and so on. These people couldn't give two. They don't really care about security. In fact, security gets in the way of them getting to market. They would put a lot of effort into eye candy. A lot of energy goes into their iPhone app. But security is really viewed as like, it doesn't matter. If we don't hit this market window, we're not going to be around 6 months from now. So who cares?
I've heard that the S in IoT stands for security.
Great, yeah. So what I'm trying to do with one of my programs called ACE, Automatic Implementation of Secure Silicon, is I am trying to incorporate inclusion of security right into the design tool process. So in other words, security infrastructure gets automatically woven in to the macro and micro architecture of the SoCs and ASICs. And it is done so almost by default. And then what you end up with is having a knob that you can turn that determines how much security do I want against supply chain attacks. How much security do I want against side channel attacks? And depending on the purpose of your device, you may not need any security. Like if you're doing a lawn sprinkler design, who cares about reverse engineering? Who cares about side channel attacks? But supply chain security, I think you would care about because you don't want this thing to be knocked off and flood the gray market and so on. So the idea here is to give people ability to trade off the normal chip economics against automatically created security by trading off performance, power, and size against security, and be able to pinpoint the kind of security, the kind of attack surface that you're worried about. And so if you were to take all the mechanisms that ACE can put into the chip and turn all the knobs all the way to the left, you will end up with a chip that has essentially no security. It will be the same as if we didn't touch it. And if you were to take all the knobs and turn them to the right, you will have probably military grade part that I would say would take 2 to the power of 100 years to break. In other words, not enough computing power in the galaxy, but it'll be 10 times as large, 3 times as slow, and you can use it as a space heater. So the question then becomes is, what is the right setting on that continuum for your particular chip, where the trade-offs between performance, power, and size match the security goals? And so my philosophy here is that I think in the 1940s or 50s, U.S. government decided that it was important for our dental health to have fluoride, but the population refused to take it in pill form, and so they mixed it into drinking water. This is sort of my goal with security. I want to mix security into the design flows, into the tools, into IP, so that whether you want to consume it or not, you're going to get it. And so the IoT companies, instead of saying, well, we don't want to spend any effort on this, actually spending zero effort on this will give them baseline security.
Yeah.
It would take them effort to get rid of it. Okay, and then people on the other side, the merchant semiconductor companies that are currently spending huge money on custom solutions, could benefit from this by saying, you know what, we don't need 800 people working on this. We can get all that stuff woven into our chips automatically. So that's basically the strategy that I'm pursuing at the functional design level.
That seems like a really good strategy to essentially say, here, just like fluoride in the water, here is the package of security that goes just natively into your systems. Have fun, basically.
But you can, as an engineer, you can imagine that it's simple to say, but integrating all of this thing into all these buses that exist in the design, into power distribution networks, and creating key registers and certificate repositories and odometers, All of that stuff is extremely sophisticated, pushing state of the art in almost every dimension.
Can you expand on that a little more?
Yeah, I can add a few more things about security here, and that is that when you think about security, you have to think about two types of attackers: the economically motivated attackers and nation states. And you have to have distinct strategies for defending against these two types of parties. Because for economic attackers, you're basically, once you make things difficult for them, they're going to go away and look at the next chip. The nation states, you're not going to dissuade them by a little bit of difficulty. So you really need to get them into the territory where they do their own math and they say, well, it'll take a million years for us to break into this. And then they go away to something else.
Is the goal to not be the low-hanging fruit and not be the easy target? Or is it more about designing things in a way that they're infeasible to hack?
I think the analogy that I would use here is if our mechanisms make the adversary spend $1 million to crack one chip, that's the win for the good guys. If they spend $1 million and crack a million chips, that's the win for the bad guys. And so where you end up between these 2 points is a matter of economics. How concerned should you be about an application? So obviously, you would be more concerned about missile control system than you are about smart toilet. So the question is then, where do you end up on the spectrum for either of these two applications?
What are some of the specific attacks that people are using to hack these chips? For example, I saw the AirTags were recently hacked. People were sending spikes, voltage spikes during the boot sequence. What are some of the tactics that people are using?
Well, I mean, what you just noted is called fault injection attack, where you use glitching to redirect flow of the code. There are very sophisticated strategies that use lab equipment, and that lab equipment, incidentally, is getting more and more advanced and less expensive. So essentially, potentially growing the hacker community. Though for nation state, the cost was never an issue. All you have to do is look at what is getting hacked the most these days. And it's strangely unchanged, probably in 5 to 10 years. The two things that are getting hacked all the time are bank cards and cable boxes. And that's because the hackers go where there is immediate economic benefit, right? And those things, I have seen demos where people are able to automatically extract PIN codes from your bank card in less than 30 seconds from any bank card. Wow. A lot of strategies at the end of the day use this notion of side channel attacks, where they're listening to emissions from the chip that are not intended. So in other words, you might take a thermal image of the chip as it's doing encryption. And you will see that the area that is hot is the crypto core. Once you have zeroed in on that, now you can now start watching the crypto core and start sending different candidate keys to it. And you will see that when the key is completely wrong, there will be one particular thermal signature. And one of the bits of the key is right, you will have a different thermal signature. And now you start varying which bit is right, which bit is wrong. And that's what the example I told you about. That's what it takes 30 seconds algorithmically to construct a key by watching thermal emissions. And you can do the same thing by watching electromagnetic emissions, watching the power fluctuations. And what I just described is actually read-only attack, where you are just trying to extract the exfiltrate secrets. The hack that you mentioned is actually the opposite direction. That's infiltration. Okay, and so I actually have multiple programs in that space as well. I have a program that is basically side channel attack simulator, which allows us to reproduce in simulation the techniques that the hackers use in the lab. And so within 24 hours of simulation, I want to see what the system can automatically extract from the design. And the beauty of this is that if you can do this in simulation, it pinpoints what design changes you need to make to mitigate what the system was able to capitalize upon. And there's the same kind of capability for fault injection. We want to be able to simulate fault injection attacks to see where are the weaknesses in the system and how can we change the design while we still can to make it more resistant to this type of attack vector. So I also have a program that looks at design rule checking for security. So in other words, analyzes the design to see if there are security vulnerabilities present. Well, I probably have at least 6 activities going on attacking secure silicon problem from different on different attack vectors from different angles. The meatiest problem, though, I have to say, has to do with Trojans. With Trojans, you have a problem of search for unknown unknowns, because by very definition of the Trojan, you don't really know what you're looking for.
Can you briefly describe what is a hardware Trojan and how does it actually get put in place?
So, as I'm sure your listeners are familiar, most of the software design today is based on putting open source components together, because you don't want to, reinvent a variety of software plumbing modules. And a lot of hardware design is done in a similar way. People integrate pieces of semiconductor IP together, and the original design portion is relatively small. So most of your chip is pieces of IP that you brought in from outside. Sometimes these pieces of IP come from past designs, some come from commercial vendors, and some, believe it or not, people go to opencourse.org and download IP from there. So the third-party IP is the absolute best carrier for Trojans. It is trivial to implant them because humans are not going to read through 15,000 lines of Verilog. And even if they do, even mildly concealed structure is going to pass them. There's no way to find Trojans in simulation. There are some formal methods that you can use, but far from foolproof. And so the easiest way for Trojans to slip into hardware design is through third-party IP. And so what they do then is they sit inside some IP block, which is connected to a bus, and they're waiting for the wake-up signal for a trigger. And so a trigger is a message on the bus that wakes them up. And trigger is something that we have a reasonable shot at looking for. So in other words, we don't know what the payload is, what it's going to do when the Trojan is activated. Sometimes it's as simple as shut down the system. Sometimes it may be more complicated, which is like send all the traffic I see on the data plane to some mystery foreign IP address. But bottom line is, we have no idea what the Trojan payload is supposed to do. And because we don't know that, we don't know what we're supposed to be looking for. So our best shot is to look for the trigger. So there's a famous case with that was publicized, I believe, in 2007 in Spectrum magazine about the Israeli attack on Saddam Hussein's nuclear reactor. So I'm not saying anything new here, but that was an example of this type of attack where the electronics for the missile control batteries were intercepted in transit by some third party and replaced with functionally comparable parts that contained Trojans that would be triggered by some external event. And so when the attack was staged, mysteriously all the Syrian missile batteries shut themselves down 10 minutes before and came back online 10 minutes after the attack was over. So it's an expensive attack, and that's why it's largely a nation-state territory. But it is really worthwhile to have those things and those time bombs sitting somewhere. I mean, from the offensive perspective.
And if you consider the cost of losing a couple of fighter jets, for example, maybe the cost of a offensive hardware Trojan looks a lot more attractive.
Yeah, but when you consider this in context of like geopolitical advantage or disadvantage, that even the price of 2 F-16s is nothing.
Where in the chip design process are the biggest vulnerabilities?
Yeah, I would say it's the IP integration, because what happens is you get third-party IP that you don't. People should have an attitude of not trusting third-party IP. Um, so okay, if it comes from reputable source, like let's say it comes from Synopsys Designware or ARM library, clearly there are reasons to accept those things. Uh, and maybe there's a next round of credible IP suppliers that you can sort of trust. But beyond that, every piece of IP comes with a test bench, which you would run as soon as you download it. And the test bench really answers the question, does this thing do what it's supposed to do? But the question of what else does it do never gets asked or answered. And that really is a great attack vector for adversaries. Believe me, we're spending a lot of time thinking about it. I have something coming up to challenge the community with this search for unknown unknowns.
So should engineers be concerned and conscious of it, or is that something that we can say, oh no, Surge has our back?
Well, I think there are some, so it's application specific, right? It depends on what kinds of things you're designing. But I would say that something like supply chain security should be everybody's concern, because that easily translates into economic advantages or disadvantages. So at the very least, people should be thinking about incorporating unique identity management schemes into their chip designs, so that each chip at the time of manufacturing has unique identifier that gets registered somewhere on the cloud and subsequently can be used for enrollment, authentication, provisioning, metering, tracking. To me, this is the least that people should consider doing, so that every piece of silicon is trackable and through its lifetime. Reverse engineering and malicious hardware, I would say this is probably not something that the commercial parties necessarily need to be terribly concerned with. But side channel attacks, this is parties trying to extract secrets from your system. I would say that's another area that your average designer should really consider incorporating into their thinking. Now, what I'm doing is going to make it easier eventually to get those capabilities into your design. In fact, at a push of a button. I haven't mentioned that the performers on my ACE program, one of the teams is led by Synopsys and ARM, which is going to mean that all of this stuff is going to be incorporated into commercial design automation tools and commercial IP. The other team is led by Northrop Grumman, which is doing variants of all of this stuff for defense applications. So one has a twist for the kinds of things that are important in defenses against the nation states, and where Synopsys and ARM focus on more commercial use cases. But bottom line is, Synopsys is everywhere. You can't design a chip these days without design compiler. And so that's how the fluoride is going to get into the water.
How much is your everyday chip designer actually thinking about security? Because in my experience, it's not really top of mind in most cases.
I think it will take some kind of catastrophe to get people to think about this in their normal course of work. When I was on the commercial side, I tried to market and sell secure silicon products, and what I found is it's like selling vitamins. The benefits are vague and distant. Threats are in real time minimal. It's much easier to sell methotrexate, like the chemotherapy medicine, okay? Because by the time the patient knows that they need it, they really need it. Whereas vitamins, so unless my doctor tells me I have to take vitamin B or die, I'm not going to touch it.
Should I be scared? Should I be scared, Serge? Is the hardware around me out to get me?
No, I don't think individuals should be, but organizations should. Well, we are already seeing, it's pretty routine, the ransomware stuff that's happening. I would say companies and organizations should be concerned. But as far as hardware security is I think it's a newish area of concern. So the parties that I'm trying to reach with this message are hardware designers. I really want them to think about this almost uniformly. Every design that has cryptography in it, there is a register that contains a key in plain text before it goes into the crypto. nobody thinks about the fact that an adversary could theoretically access those lines of metal on silicon and extract that key before it gets encrypted. This is just one of 100 examples of the data in transit and data at rest is exposed. All it takes is a dedicated attacker to gain access to it. And so to some extent, we've been sort of fortunate that it's not easy to monetize this stuff. Like, for instance, there was brief concern about hacking cars, and so you know why that nothing more happened with that? There's no economics to support. There's nothing to gain here. So the hackers showed off their amazing prowess, and then what? They went back to attacking bank cards and cable boxes because that's where the economic benefit is. And so to some extent, we're fortunate that in the areas where their economic model is not present for the hackers, they're not going to touch it. And like everything else, economics defines the behavior in this space.
Fascinating. Are there any highlight standout projects in your career with DARPA or career before that are extra special to you or that the audience would find kind of extra cool?
Well, I would say that I've had some interesting experiences in my career. I was lucky to be around Silicon Graphics in the early days of movie special effects. So we had James Cameron come and work at Silicon Graphics when he was making The Abyss and Terminator 2. And so I was participating on the fringes of that activity. That was a lot of fun. And that's probably the coolest thing that I can tell my kids that they would enjoy, that I somehow was peripherally involved with Terminator 2. The people I meet at DARPA are fascinating. There's literally any topic, no matter how bizarre or remote, you'd say, hey, is there somebody in the building that knows about it? And the answer would be, yeah, this guy on the third floor, he wrote the book. Like, what, a book? The book on this. And the other thing is you meet people that are doing some things that like are just striking in the sense that you never would have thought about this. So I met somebody at DARPA who is a marine biologist. And I immediately was interested. So what's a marine biologist doing here?
Right.
And this person told me about a bunch of things that were sensitive, but one of them she thought was kind of routine. I found kind of fascinating. And so the conversation went something like this. She says, I work with shrimp. I said, well, I'm not sure I understand that other than like Red Lobster context. And she says, well, do you know that shrimp actually talk? I'm like, what? Well, apparently shrimp communicate in discernible patterns. And I said, okay, so why is this interesting or important? And she said, well, their communication changes in proximity of large metal objects. I get it. Anti-submarine warfare.
Yes, the shrimp have spoken.
Exactly. So, and then it turns out it's not just shrimp. It's all kinds of things in the sea that have particular communication patterns that could be interpreted for some useful data. And apparently, in that world of marine biology, this is all widely known. I had no idea.
So it's almost like you have a shrimp side channel attack and a shrimp side platter at the same time.
That's right. I have shrimp two ways. Yeah. But I would say this. I just wanted to close with this observation. So when I came to DC, I had kind of a caricaturish way of thinking about the government, largely inspired by House of Cards and VIP television shows. And so I had this certain cynicism about the government. And very quickly, in engaging in conversations with people around the government ecosystem, I was stricken with this observation. These people actually think the system works, which was a striking discovery for me, coming from outside of the Beltway. And so And from that day on, I have kind of marveled at the commitment of the people in the government. I have not met anybody who just phones it in. Everybody I've met in the government is really focused on the mission. People really believe in the system. They really care. And particularly the people in uniform that I have met, I have, again, I viewed that sort of dismissively before I had any kind of firsthand contact with them. But once I started meeting people in uniform, I have just been totally blown away by the quality of folks we have serving the nation without any clear, economic benefit to themselves, and doing so because they believe in America, they believe in the mission. And so, to me, that has been like the most important takeaway. Something I would have joked about, 4 years ago, and now I look at it through different lenses.
Comforting words to end a hardware security podcast. Thank you, sir, so much for your time. It's really been a pleasure having you.
Yeah, outstanding. I enjoyed it. Thank you.
DARPA has changed its name a couple times over the last few years, so I've officially submitted to the US government a proposal that they change their name to LARPA. It's basically DARPA, but with more live-action role-playing. We'll see how that pans out. You can find this and all other episodes of Moore's Lobby on allaboutcircuits.com. I'd like to give a huge shout out to Dave Finch, who hosted the first 2 seasons of this podcast. Good luck in your future endeavors, Dave. Also, a huge shout out to you, the listener, for making this possible. If this is a podcast you like and you made it to the end of the episode, so that's pretty likely, you can give back to us by sharing the Moore's Lobby podcast with at least one other person that you think will like it too. You can also give us your feedback on the All About Circuits page, leave a comment, or hit us up on LinkedIn or Twitter at Daniel Bogdanoff and at All About Circuits. I'll catch you in the next episode where I get to ask the CTO of NVIDIA why it's so stinking hard to buy a graphics card at MSRP these days. On behalf of EE Tech Media, I'm Daniel Bogdanoff. Thanks for listening.